We talked about, at the end of yesterday, we talked about races to infinity. So we said which is going to grow faster. So for example, we had x versus x squared. And we decided that x squared is going to win that race. X squared grows a whole lot faster than x does. If I take a number and square it, that's going to get bigger faster than just having the number itself. Same thing for like x squared versus x cubed. X cubed would win because cubing a number grows faster than squaring it. So we can do some other practices with that. But what that relates to is talking about asymptotes. And this should be review. This should be something you've seen before, but we're going to talk about it in terms of limits. So in this race, if the bottom wins, so for example, if we have x over x squared, then the limit as x approaches positive infinity, this is what we talked about at the end of yesterday. The limit as x approaches positive infinity, since x squared wins, since x squared is growing faster than x, as numbers get bigger and bigger, this whole thing gets closer and closer to what? 0. Right? Because this gets a lot smaller in comparison to the x squared. So that limit as x approaches infinity gets to 0. So that means that the horizontal asymptote is at y equals 0. If the top wins, so for example, we had like x to the 4th over x cubed. As x gets bigger and bigger and bigger, really big, what's going to happen to y? It's going to get really, really, really big. Because x to the 4th is going to get bigger a whole lot faster than x to the 3rd. So that means that it's going to keep growing and growing and growing. That means no horizontal asymptote. That's if the top wins. If there's a tie, so let's talk about that. So let's say on top I had a 3x squared, and on the bottom I had a 5x squared. Who wins, top or bottom? Bottom, but not in the same way that the bottom won here. Here it's just the lead that it takes is just out of control. Right? The lead that this starts to take is, it starts out a little bit ahead, but then it's going to grow way, way faster. Versus the lead that 5x squared takes over 3x squared stays relatively consistent. And so as I plug in really big numbers, if I have an x squared, these x squareds tie each other, And the thing that starts to matter is that there's a 3 on top and the 5 on the bottom. And so as I get bigger and bigger and bigger, then the ratio of the top to the bottom, let's say I get 1 million out for the x squared and 1 million out for the x squared down here, then we basically have 3 million over 5 million. Or 3 billion over 5 billion. And this is going to end up being 3/5. And so y equals A over B, where A and B are the lead coefficients. Do you remember what lead coefficients are? So the coefficients in front of the largest polynomial term. So those are our kind of 3 different situations that we could have. And the way that we usually talk about that is the degree on top versus the degree on the bottom in Algebra 2 or pre-calc class. But in terms of calculus, we can talk about it in terms of limits as we go to infinity. So that's why we're talking about it now. So to put it in a more kind of formal way, and we'll actually practice these here, just to give you an idea. And then we'll do some examples where we put this all together. All right. Case 1, degree on top is less than the degree on the bottom, then it's y equals 0. So that's if the bottom wins. If they're the same, asymptote is the ratio of the lead coefficients. That's if there's a tie. So this is the bottom winning. This is that's an M. This is a tie, and this is the top winning. So let's actually do these examples, just so that you see how these work. On 92, we have x squared minus 2x plus 1 over x cubed plus x minus 7. So who's winning there, top or bottom? Bottom. So if the bottom wins, then horizontal asymptote is at y equals 0. 93, who wins, top or bottom? The top wins, and so that means no horizontal asymptotes. 94, who wins, top or bottom? Top, so that means no horizontal asymptotes. But we do have, oh, hold on. Something's wrong there. I just caught it. Who else caught it? It is. The lead term here is not the 4x. The lead term here is the negative 3x cubed versus 5x cubed. So we have a tie. Tie goes to the lead coefficients. So y equals negative lead coefficients. So 5 on top, 3 on the bottom. So we do have a horizontal asymptote there. So be careful if it's not in standard form. You want the largest degree. Those are what you want to compare. Even, here's why we don't, we got a 2x squared here. Why don't we talk about that? Well, because when you start to get really, really big numbers, cubing something is going to matter a whole lot more than, say, adding 8. Okay? If I, if I were to ask you, a trillion cubed, and give you an estimate of that, it would be 10 to the 18th. And be like, oh, but you're off. You're way off because you got to add 8. Well, once you have 10 to the 18th, adding 8 isn't going to do a ton. Same thing for if I took a trillion squared. If I took a trillion squared, trillion cubed is 10 to the 27th. And then I have 10 to the 18th, which is not that big in comparison to, it's like taking a million and then giving someone another $100. It's like, okay, I have another $100. I already have $1 million. So once we start getting to really, really big numbers, what may seem like a lot, like squaring, doesn't start to matter. And all that really starts to matter is these terms that shoot out into the lead. So those lead coefficients and these lead terms are what's going to matter. So look for your largest degree and go at it from there. Now, even if these don't have horizontal asymptotes or anything like that, we could still have a vertical asymptote. For example, anywhere the bottom is 0 here, which happens at plus or minus square root of 7, that's going to have vertical asymptotes. So what we're going to end up doing here is using all this information to give us a rough sketch of what the graph is going to look like. All right, and that's what we're going to do with these last couple examples. Here we go. Okay, which one do we want to do here? Let's do this one. Yeah. Okay. Let's start with horizontal asymptotes since we were just talking about them. Horizontal asymptotes. Who wins, top or bottom? Bottom wins, and so that means that our horizontal asymptote is at y equals 0. So horizontal asymptotes at y equals 0. Let's factor this. So I have GCFs that can come out of each of these. So I've got, on top, I have a 4 that I can take out of the top. So I got x squared plus x minus 6. On the bottom, I can take an x out. And then I have x cubed minus 2x squared minus 9x plus 18. Well, the top is pretty easily factorable. Let's see. I want to multiply to be a negative 6 and add to be a positive 1. That's going to be a positive 3 and a negative 2. X plus 3 times x minus 2 on the top. Any ideas how to factor the bottom? Anyone know how that bottom is going to factor? It's algebra 2 time. Idea? Grouping. Yes, that is how we're going to do it. So we have x cubed minus 2x squared. Nailed it. 2x squared minus 9x usually the microphone doesn't pick up a lot, but I'm thinking it might pick up Padilla. We'll have to see. Okay. So here's the idea of factoring by grouping. And part of what I did was when we were in geometry and I taught you factoring, I actually used grouping to teach you factoring, which was to split this into parts and see what can come out of each group. And then what we should end up with is a matching factor on each of those parts. So I have what can come out of each of those groups. So I have an x cubed and a minus 2x squared. So I've got an x squared that can come out of each of those. And when I take an x squared out, I'm left with x minus 2. And then I've got minus is the first thing I see, so minus is the first thing I'm going to write. What can come out of common factor out of this second part? A 9. And then I have an x, since I took a negative 9 out, minus 2. And the thing that makes this grouping work is this common factor of x minus 2. So I got x squared and then minus 9 times the same term. So I can take that same term and just factor it out. Take the x minus 2 and factor it out. And what I'm left with over here is an x squared. What I'm left with over here with is a minus 9. Oh, well, I can factor x squared minus 9. It's x plus 3 times x minus 3. So that's how that factors. That's by grouping. So let's put that in. If you wanted to do like a long division or a synthetic division or something like that to get the factors, it'd still work. You'd still get the correct answer here. Okay. So let's talk about what's going to happen here. Vertical asymptotes. Vertical asymptotes happen where the bottom is 0 and the top is not. Where the bottom is 0 and the top is not. So where does that happen? There's two places. Bottom is 0, top is not 0. So we have, basically you're going to use the factors that don't cancel on top and bottom. So that's the x minus 3, which will make x equals 3. Then I have this x over here, so that'll translate into it being x equals 0. So what's happening at x equals negative 3 and x equals a positive 2? Remember when we factored and canceled on top and bottom? What was happening in the graph there? We did that when we were talking about limits earlier on in the week. and the limit turned out to be a specific number. So that means we're approaching a specific number, but the graph doesn't actually exist at that number, but it's getting closer and closer on either side to a specific number. These are holes in the graph. So there's a lot going on in this one. But here's the ideas. Horizontal asymptote, you race the top with the bottom. Since the bottom 1, y equals 0. Vertical asymptotes is where the bottom is 0 and the top is not. So you don't have any canceling. Those are the places where you're going to have a vertical asymptote. Then the holes in the graph are going to be where you have those factors that cancel. So so that we want to figure out where that hole is, figure out the limit as x approaches -3 of f of x, and give me the limit as x approaches 2 of f of x. And another thing we can do is use the limit as x approaches 3 and 0 from the left and right to figure out where how things are going to behave around the vertical asymptotes. We practiced that on yesterday. That's what we spent yesterday doing. So limit as x approaches -3 and limit as x approaches 2. I've done all the hard work for you because I figured out how to factor it and then I canceled. And so all you have to do is take this new thing and plug in those numbers. This is what we're plugging the numbers into. So -3, that's going to be -3 times -6 is going to be a +18. So that's going to be 4 over 18. That's going to be 2 over 9. And then I have limit as x approaches 2. That's going to be 2 times 2 minus 3 is -1. So 2 times -1 is going to be -2. So 4 over -2. So that's where the holes in the graph should be. Which means I typed something in wrong here. there we go. Okay, where's 2? 2 is there. There's -2. Just double checking. -3. There we go. So this isn't going to show the holes in the graph, but it is going to show the asymptotes and that behavior. Here's what the graph looks like. It doesn't like the vertical asymptotes, so it's trying to like connect things. You'll see that happen if you put these things in the calculator sometimes. And you could actually do this and determine what the limit as x approaches 0 from the left and right are. You could find that the limit as x approaches 0 from the left is going to be positive infinity, and the limit from the right is going to be negative infinity. And be able to draw kind of a rough outline, a rough sketch of what this graph will look like. And you'll notice that horizontal asymptote is at 0 as we get farther and farther out to the right. So that is the behavior of our graph. If I zoom in a little bit, you won't be able to see the hole, but it is there. And it's where we expect it at 2. We're at -2. And then at -3, there's our positive 2/9. So that's what that graph looks like. And so notice that using the ideas of the limits and the asymptotes and the holes in the graph and all the things we've talked about so far about limits, we can get a very good rough outline. And we could do a bit more if we had more time to fill in more of these details and get an even better picture without even looking at the graph of what this is going to look like. So it can help us determine the behavior of these types of graphs.